Recall that the Laplace transform of f of t is defined by the improper integral from 0 to infinity of e to the power negative st times f of t dt. In other words, to find the Laplace transform, we have to evaluate an improper integral, which oftentimes involves integration by parts, and this can be a tedious task. In this section, we will discuss some properties of the Laplace transform that will simplify its computation. These new properties will also enable us to use the Laplace transform to solve initial value problems. The first theorem states the following. If the Laplace transform of f equal to capital F of s exists for s greater than alpha, then the Laplace transform of e to the power at times f of t is equal to capital F of s minus a for values of s that are greater than alpha plus a. So multiplying a function by e to the power at results in a shift in the Laplace transform. And the proof is pretty straightforward. So if you take the Laplace transform of the function e to the power at times f of t, then by definition, this is equal to the improper integral from 0 to infinity, and then e to the power negative st, and then times e to the power at times f of t dt. Now we can manipulate these two exponential functions and combine them, and it will look as follows. This then is e to the power negative s minus a times t, and then times f of t dt. So what we see here is almost the definition of the Laplace transform of f, but it's not at s. The s here is replaced by s minus a. So this is actually the Laplace transform of, and then f of s minus, the Laplace transform of f of t, but then evaluate it at s minus a. And we can also write that as f of s minus a. So let's see this translation in s at work in an example. So we want to find the Laplace transform of the function f of t equals t to the power n times e to the power at, given that the Laplace transform of t to the power n is n factorial over s to the power n plus 1. So what we'll do is we'll let capital F of s represent the Laplace transform of t to the power n. So this is equal to the Laplace transform of t to the power n at s. And we know that that is equal to n factorial over s to the power n plus 1. That's given. So then the Laplace transform of let's say e to the power at times t to the power n of s is given by f of s minus a. So what that means is that instead of plugging in s, we're going to plug in s minus a in this function here. And so that is equal to n factorial over s minus a to the power n plus 1. Now, the next theorem is why Laplace transforms are so good for differential equations, because it turns out that the Laplace transform turns differentiation into multiplication. So if f of t is a continuous function on the left closed interval from 0 to infinity, and the derivative of f is a piecewise continuous function on the left closed interval from 0 to infinity, and both of these functions are of exponential order alpha, then for all s greater than alpha, we have that the Laplace transform of the derivative of f is equal to s times the Laplace transform of f minus f evaluated at 0. So we'll prove this, and it basically depends on the integration by parts. So if I take the Laplace transform of a function f prime of t, so I want to find the Laplace transform of f prime of t. Again, by definition, that is the improper integral from 0 to infinity of e to the power negative st times f prime of t dt. Okay, so what we're going to use here is integration by parts. So I'm going to compare this with the integral from 0 to infinity and then u dv. And that is equal to u times v evaluated at infinity and 0. And I'm leaving off the limit as n goes to infinity here for convenience. And then minus 0 to infinity of v du. So what I'm going to pick here is that on the right, I'm going to pick u equals e to the power negative st. And so what I will need later on is du. So let's see what that is. So if I look at du dt, I take the derivative of this and I get negative s by the chain rule times e to the power negative st. And so if I solve that for du, I get that du equals negative s e to the power negative st, and then dt. Also, if I let dv be equal to f prime of t dt, what I get is dv equals f prime of t times dt. And so by dividing both sides by dt, I actually get that dv dt is equal to f prime of t. And so that means that if I integrate both sides, that v is actually equal to f of t. And so these are my ingredients for my integration by parts. So on the next line, what I get is u times v, and u is e to the power negative st, and then v is f of t. And then I'm evaluating that at 0 and infinity. And then I have to subtract from that the improper integral of v du. So v is f of t. And du is over here. So that is equal to times negative s e to the power negative s t dt. Okay, now my first part here, I should be using a limit as n goes to infinity, but let me just plug in infinity. So if I plug in infinity into that first expression, I get e to the power negative s times infinity. Again, infinity is not a value, and so we should really think limit as n goes to infinity of negative Sn, but I want to keep the notation compact here. So it's negative s times infinity, and then I'm plugging infinity into f. And then when I plug in 0, that's a lot more straightforward. I get e to the power negative s, and then plug in 0, and then times f of 0. And then the second part, this is an integral in t, so I can move the negative s outside, and that actually gives me a positive s. So I have plus s times the improper integral from 0 to infinity. And then what I'm left with inside there is e to the power negative st times f of t dt. So these parts, this is pretty straightforward that is just f of 0. So I have a minus f of 0 here. For the second part, I have s times, and what I have here is exactly the definition of the Laplace transform of f of t. So this is plus s times the Laplace transform of f of t. So now let's worry about what is happening here. So f of infinity is something that could potentially blow up, right? If f goes to infinity. But we know that f is of exponential order alpha. So what that means is when we plug that in, infinity here, this whole thing goes to 0. So the short answer here is that that first part is 0, as long as s is greater than alpha. And again, that follows from the fact that f is of exponential order alpha, and it cannot grow too fast. And so as long as you make s bigger than that, this whole thing will go to 0. So what is left here for the final answer is just s times the Laplace transform of f of t, and then minus f of 0, which you can think of as an initial condition. So we proved that the Laplace transform of the derivative is equal to s times the Laplace transform of the original function minus f of 0.